continuous, batch, or even periodic, it's always assumed that the raw materials and the utilities are always available. And that is not really true for renewable energy. So that brings us basically to a few important R&D questions. Yeah, how to frame operation mode selection for a solar fuel plant, how to determine the best operation mode for such a plant, and if we know in the end, hopefully, the way that we operate such a plant, then yeah, we can talk about what really influences the operation of a solar fuel plant. By the way, what I'm presenting is already in a paper, and the reference to the paper you can see below. So let's do a simple example. This is a solar methanol plant. So basically we start on the power, and we are allowed to basically route the power either directly to a methanol process or via large-scale battery storage, because that's typically what we would need if we want to basically continue the production overnight when there is no solar energy anymore. And the circular methanol process is basically consistent out of three units: direct air capture, that basically takes CO2 from the air, hydrogen production via electrolysis of water, then basically hydrogenation of CO2 with hydrogen to methanol and water. So basically we need one separation step where basically methanol and water are separated, and then we basically have a rundown to a methanol tank. Now, if you think about this process and we go back to the original question about operation, then two extreme modes of operation can actually be foreseen. Coupled operation, that basically means the methanol process simply follows the solar profile. That really results in highly dynamic operation, because in the end, during the night, it means turning off your process. The other side, the other extreme, is decoupled operation. Somehow the battery storage is capable of actually maintaining steady state operation. So regardless of day and night cycle, you are basically running your production rate independent from your solar profile. And then if you start to think about the pros and cons of these different kinds of operations, so coupled and decoupled, then basically let's focus on coupled operation and the pros. If you have coupled operation, you profile and you take, then no battery storage is needed. Since you don't have routing of electrical power of your battery, there's no effect of the round trip efficiency of a battery, which is high, but certainly not 100%, order of magnitude 80 to 90%. If you take a look at the pros of decoupled operation, then it allows for an operation mode that we know very well, semi-steady state operation. It also gives you high process equipment utilization, because if you want a certain average capacity and you run always steady state at that capacity, you don't need any over design. Your design capacity over your average capacity is very close to 1. That's not the case if you go for coupled operation, right upper part of the curve of the table. If you want a certain average capacity, then your design capacity needs to be twice your average capacity, because during the night you're not producing anything and you need to compensate for that during the day. So if you roll this up in an economic way, there's really an intricate trade-off between the various, for instance, capital expenditure for battery storage, the capital expenditure for methanol process, and the OPEX in the sense of how much power, how much electricity do I need to use. So that basically already is a clear indication you could solve this problem using optimization. About operational flexibility, I always said that if you have coupled operation, you really need a lot of operational flexibility. That's basically depicted in this picture. On the horizontal axis, you basically see time, and on the vertical axis, you see the production rate. And normally for any kind of plant, existing plant or new plant, you will have limitations. Limitations with respect to turn-down ratio, which is basically defined as the maximum production rate over the minimum production rate. And for conventional designs, it's just 2. So if you have full load 100%, you can typically go back to 50%, but not more than that. But what is also important is how fast can you ramp up or can you ramp down basically your plant, if you want to follow basically your solar profile. The normalized ramp rate, that's basically the normal, that's the ramp rate divided by P max, is just about 1% per minute and typically much less. So it takes hours to ramp up a plant to full capacity and to ramp it down again. And the reason why we can actually do this for conventional plants is that we have several weeks of storage on the raw material side as well on the product side. So what you do in between those two tanks farms is up to you and can be very slow. So how are we going to solve this? Well, I just given the overall picture of a solar fuel plant. As a matter of fact, it was a solar methanol plant. In order to get to something that we can actually understand, but also something that is computational tractable, we need to have a simple model. And I'm going to make a very simple model by making two assumptions. I will look at a solar fuel plant from an energy storage and conversion perspective. And I'm just saying on the unit operations that I'm looking at, I either have storage, for instance, the methanol tank, or the battery storage, or I have conversion. For instance, the methanol process actually converts the energy from power to chemical energy. And then the next step is, if everything is energy or the equivalent of energy, I just can lump the storage and conversion dynamics using basically single input, single output energy transfer functions. If you do this, you can actually formulate what is known as an optimal control problem. What I'm trying to minimize is basically the total amount of my cost, and I have a number of constraints over there. I have the availability of solar power. I have basically my solar plant dynamics, given by the transfer functions we just discussed, and I have a number of operational constraints. For instance, the turn down, the ramp rate, but also a required methanol production. As it is formulated over here, it seems to be a classical optimal control formulation, but actually it's not. Because if you really take a look at this detailed formulation, it contains operational degrees of freedom that are related, for instance, to the routing of power, design degrees of freedom, which are related, for instance, to the battery size and the capacity of the methanol process. So for that reason, the word extended is used. The normal operational degrees of freedom are extended by design degrees of freedom. The problem can be solved, but we need two transformations to do it. And then it can be solved using the simultaneous approach. This is the result that comes out of it. On the horizontal axis is basically time in hours, and we basically do 4 times 24 hours. At t is 0, we basically have our first sunset, which you can see in the blue curve, because sun comes up, so the intensity of the solar profile increases, and 12 hours, 6 hours later, you basically have midday, so maximum intensity. In green is basically how your methanol process reacts to it. In yellow is basically the charge that we need in the battery to do this. And the brownish curve, the methanol tank basically fills over time. Now, if we assume a cost structure by 2030, an average production rate of 100 tons of methanol per hour, there is no constraint with respect to turn down ratio. And as said before, we basically take 4 days, then this is the outcome. It really shows that the methanol process really follows the solar profile. So from an economic point of view, coupled operation is really preferred. And the highly dynamic operation that results from this is really indicated by a turn down ratio of 9, which is very high compared to conventional process operation. The other things that are resulting from this simulation, optimization, I should say, is that the overall efficiency is close to 50%. So 50% of the electrical power ends up in the methanol. And the manufacturing cost of methanol is around $1,000 per ton. By the way, this in methanol terms is a large scale plant. In fuel terms, this would be a small plant, by the way. The fuel market is very big to the chemical markets. So it's important to keep that in mind. But still, for a plant like this, for 100 tons per hour, that in order to maintain operation at a minimum amount of energy input to avoid shutdown overnight, which is 1,000 gigajoule per hour, as you can see in the notes. Yeah, it really takes a substantial battery system. Yeah, and just to give you a feel for it, it would be 25 times the Tesla big battery, just to avoid shutdown overnight. And the reason why we want to avoid shutdown overnight is because a cold startup really takes many hours. Yeah? And that does not allow us to follow the solar profile. If you start playing around a little bit with the process economics, more specifically with operational flexibility, so turndown ratio and ramp rate, as we discussed before, then it's very clear in this picture, by doing more optimization runs, the value of operational flexibility. For very high turndown ratios, in green 8, yeah, but also high ramp rates, yeah, 4,000 on the horizontal axis, basically, yeah, you get below $1,000 per ton of methanol. However, if you reduce the ramp rate and at the same time you also reduce further operational flexibility by going for a lower turndown ratio, for instance 2, conventional turndown, basically the cost of methanol actually shoots up to $1,200 per ton. And that's basically because battery storage has to compensate for the lack of operational flexibility, and that basically is reflected in a higher methanol price. So to conclude, and also give a little bit room for further work, I think from a process system engineering perspective, solar fuel plants really pose interesting new challenges, like, well, how to operate such a system that is driven by intermittent renewable energy. And I think with the work I just presented, at least we scratched the surface. But there are other important questions to be asked from a process system engineering point of view. Yeah? How to design and control new unit operations like electrolysis, which are part of this scheme. And I've just given you on the left-hand side below basically a PNID, so a process instrumentation diagram, which shows you the base layer control of an alkaline electrolyzer unit operation. And you can see there is actually quite a bit of control involved to get this up and running. And also to allow for the right operational flexibility, the process together with the control has to be examined, yeah, and has to be designed that you get the operational flexibility that you want. Last but not least, I also shown you basically a price, yeah, by 2030. That was an estimate, but we think it's a reasonable estimate as the price of methanol. $1,000 per ton is really much more expensive than the current prices that we've seen for methanol. Historical prices for methanol really vary between per ton, and that basically means that $1,000 per ton is way too expensive. So we have to find ways to reduce the cost of solar fuels and chemicals further down to affordable levels. I think there are 3 ways of doing it. Yeah. From a scientific point of view, we can basically look for better materials that increase efficiency of solar cells, give better selectivity and single pass conversion, for instance, catalysts. You can also develop prototypes that are related to flow sheet, let's say flow sheeting, better integration operations, process intensification to make things cheaper. And I think going from the indirect route to the direct route is basically a good example of using process intensification. And then last but not least, if you really go to the high scale, and fuels are also in the future a very large scale market, then you can actually make use of the fact that scale up offers also economic advantages. If you do scale up by size and or number, we know that in all cases you can actually get big reduction in the cost. A good example is basically how the cost of solar fuels have come down. It is somewhat related to the increase of efficiency, but most of the price reduction that we've seen is really due to mass manufacturing of solar fuel. With that, I would like to end my presentation. Thank you for your attention, and I'm happy to take any questions.
Thank you, Adri, for this presentation. So there were some questions, I think, popping up in the chat section. I would like to ask Johan to
Yes.
look at them and make a selection, but I may also start with my own, which I also post.
Indeed, that you start, Anita, because you were also the first one with a question.
Yeah, because it is clear that there is a big challenge on this intermittency of the availability of the energy source. But on your very first slide, I saw that it is solar power that you are using, which means that it does not matter where the power comes from, because power is power. So you may also use wind power, which is also renewable, but you also may just use other power available, maybe to get a constant power supply and to avoid any of the difficulties you're trying to solve.
Yes.
Why did you consider that?
No, it is being considered. It was not directed part of this study, but let's start with wind energy. It is true that sometimes the wind blows during the night, of course, but still, if you take a look at the availability of wind power, although perhaps it doesn't show a very clear day and night cycle, there is still the influence of let's say not always being available. So you still have to go up, even if you use wind energy, you still have to go up with the wind increasing and decreasing. And that, I think, what is also important is the price of that renewable energy. If you start to look at other sources which still have to be renewable, if we still take decarbonization as a starting point for making these plants, I don't think there are that many options besides solar energy and wind energy to come to a decarbonized solution which also is affordable.
No, that's true. But in the meantime, you could start with also partly using fossil electricity and then simultaneously trying to switch and intermittency problems. So
yes,
but that was just a suggestion. Johan.
Yes, so I think the next question is from Nikhil John. Perhaps he can unmute himself and ask the question.
Hello, can you hear me?
Yes, we can. Yeah.
Hi, thanks for the presentation. Very interesting. I have a question more on the kind of related to the barriers of this technology from the economic or demand side of the industry. So this flexibility aspect, how radically different is it from the way conventional methanol is produced in the sector? And does the industry kind of have to change the way it operates in terms of like contracts for delivery of methanol? Are they different from conventional, or are there other demand side structures that are different from this as opposed to the conventional way methanol is produced?
Okay, thanks for your question. I think there are two elements to your question. Let's take the first element. So how different is this operation that I've shown from, let's say, conventional methanol plants? Well, conventional methanol plants are really operated in quite a semi-steady state way. So the turn down for most methanol plants is really only 2. So a turn down ratio, what I've shown you of 9, is really much higher than conventional plants. And we can design, I know from experience that you can design for higher turn downs, but it will also cost you more. There are very good technical reasons for that. The other part of your question is what does it really mean for the methanol side? Well, once you have produced methanol, which is a liquid at atmospheric conditions and temperature, you can store it very effective in large tanks. So once you have methanol, once you have a dense energy carrier, I think things are pretty normal from then on. Let me also add a simple example why process systems have limited turn down. Let's take a heat exchanger example. In order for a heat exchanger, for instance, to be really effective, you want high transfer coefficients. You want a high transfer coefficient on your utility side as well as your process side. So it basically means you would like to have turbulent flow on both sides. On the moment that you basically go from high production rate to low production rate, basically on the process side, you will start to diminish your flow, and you will have, at one point in time, you will basically have the transition from turbulent flow to laminar flow. And your heat transfer will actually be much, much less, not a little bit less, but much, much less. For that reason, and other reasons as well, systems really have limited turn down, also for economic reasons. You can design a heat exchanger to have a high turn down, for instance, by having an external recycle. It's even used in real practice, but of course you can imagine that adding an external, adding a recycle of that heat exchanger system. I hope I answered your question.
Okay.
Yeah, thanks.
Thank you. I would like to do one last question of, well, good challenge to pronounce it, Gianluca Carici. Gianluca Carici, can you pose your question?
Oh, hello. I've asked a few, so I'll ask the first one. So you are thinking of using batteries for supplying energy overnight when the sun isn't shining. What about using your hydrogen production plant, making it slightly bigger, and then use hydrogen through a turbine for producing that energy? How does economically compares with batteries?
Yeah, no, it's very good. I like your question. I think one of the advantages of indirect route is that we actually make intermediaries like hydrogen, which can be stored. So you're quite right. Yeah? What could be added is basically in the framework is the possibility to add storage, for instance, for hydrogen. Of course, the question that arises, what is really the cost for storing hydrogen? And depending, I think, where you are, if you can make use of, let's say, advantageous subsurface storage possibilities, for instance, southern caverns, like people talk about, it might be quite cost effective. But if you don't have that subsurface possibility, I think the storage of hydrogen, certainly large-scale storage of hydrogen, might be expensive, and there's also a safety issue. But it can be the framework is powerful enough to be added as an extra option.
Thanks. Thank you, and also thank you. I think this was the last question because we have to continue. I would also like to ask all the others that are posing a question. It is impossible to answer them now, but we will make sure that the questions will go to Adri so that he can still maybe answer them one-to-one to you, because we have seen who post the questions. Anyhow, I think it's interesting to see that there are many potential design parameters in this whole process with hydrogen and wind and other energy sources to make it successful. So I hope that we can soon see it being scaled up. I would like to continue to the next part of this meeting, which is the panel discussion. So next to Adri, I would, yeah, you can keep that on the screen, Eva. But I will introduce Simon Jagers, Tim Offermans, and Niels Deen. During this panel discussion, you will be asked some polls, so you can go to the next slide, Eva. So while I'm introducing Simon, Tim, and Niels, the people can start trying to get their mobile devices on and go to the to the Poll Everywhere website. So go to pollf.com, enter ISPT warmte 673 as the event code, and then you will get questions later on. But first, I will introduce Tim and Niels and Simon. Tim is a PhD student at the Radboud University, and his research is focused on facilitating automated process control of chemical reactions. We have Niels Deen, who is a full professor at the TU Eindhoven. I can tell a lot about what he is doing at the Department of Mechanical Engineering, but I think most relevant for you to remember that he is behind those metal fuels that were also on television today at one of the beer producers in the Netherlands that is testing this metal fuel. So you may get some questions, Niels, about that one. And then we have Simon Jagers, who is leading an SME on data, on turning data into actionable information. And his SME is especially focusing on improving the reliability of motors and other rotating equipment. So there will be 4 people in the panel, including Adri as well. So before going to that discussion, I hope you have all managed to find the PolF website and enter the event code. So we go to the next slide and we go to the first question. The panelists have not seen this question, so it's nice for them also to prepare. Question is, what is the main motivation for the energy transition? And be aware you are only able to give one of these options. So answer A is declining fossil resources. B is increasing energy demand due to growing population and wealth. C is mitigate global warming. D is reduce pollution of our natural environment. And E is the high potential of alternative energy sources. Well, we see that there's one really exceeding here. But I would like to pose a question to Tim.
Yes, of course.
Do you think it really matters what the main motivation is?
I think it does matter what the main motivation is, also because energy transition also starts with just, the people on the street, so to speak, and you have to convince them, and to convince them you have to give a good motivation, I would say. So I think it matters a lot. But in general, I think maybe it's a bit cheesy, but my main motivation would be just that we have to take care of our planet, and that kind of overlaps with a couple of these answers. Indeed, mitigating global warming is very important, because otherwise we'll lose a lot of land to live on, but also just general reduction of the pollution of the air that we breathe, and also the earth, that also attributes to that general goal, I would say.
Yeah, but it means that for yourself, your own personal motivation is this global warming thing, and you also think that it's crucial that we motivate the people on the street with the right incentive, in fact, for doing something about this.
And maybe also for myself, I mean, declining of the fossil resources. Sorry that I don't give one answer, but it's obviously a very complicated question. But declining fossil resources is also actually maybe even a larger motivation, because at some point those will be gone, and then we don't have any energy more to consume. So by then we need to have been transitioned to something that is sustainable.
Yeah, that's true. Looking into the rest of the panel, would you also have been chosen for C, or who of you would have chosen for one of the other options?
I would have chosen for something that's not even mentioned here.
And what would it be?
The mix. Well, the geopolitical unrest that is typically a result of of lack of fuels. I think we had an election yesterday where one of the main candidates was vehemently against energy transitions, or certainly against more sustainable practices. I think it's high. I mean, anything that would make us more self-reliant, and specifically anything that makes us more reliant on natural or renewable sources, would be something that would highly motivate me.
I can imagine that, but it's a typical question, a typical answer also from somebody from industry who risks not getting sufficient energy. I can imagine indeed. How do you see that, Adri?
Well, if I make the connection also to something that has scored very low, the increasing energy demand due to growing population and wealth, of course, we are in a very fortunate position here in Northwest Europe. We do have the availability of sufficient energy, but that's certainly not true for the rest of the world. And directly related to the energy transition is that if you talk to people, for instance, in India or other countries, they're not so much concerned about the energy transition, but they're far more concerned about getting energy in the first place.
And if our people in the audience that also would like to add another motivation, please raise your hand and also put your motivation in the chat so that Johan can warm me. But then looking, Niels, because you are also working on a new energy source, this metal fuels. What is your main motivation to do that?
Well, maybe to start with the question on the screen, I think whatever your motivation is maybe not so important as long as you mitigate global warming. And it's really an issue that is important for all of us, particularly here in the Netherlands, where we are very close to the sea. We are at low sea level, so rising sea levels is really an issue for the Netherlands, or it will become an issue for us. So that's for us already a good reason to do something here. And so all the other reasons are all very valid, I would say. But the most pressing one for me is the global warming. And yeah, when it comes to looking for solutions, I think what is very interesting is that what we just heard from Adri, that methanol could be a very interesting energy carrier for particular applications. So you can use it as a base chemical, but also as a fuel. Production of hydrogen is another one. Using metal fuels is yet another one. But there is no silver bullet. So we have to work on all these different solutions to make sure that we can energy system which where we can also prevent global warming. So that's my take on the story.
Yes, thanks a lot. Let's see. Peter Dowdy in the call. You have something to say?
Yes, I also put it in the chat. I think the great way in which we dig all kind of natural stuff and make products out of it is directly causing pollution in the end. It's an enormous amount of material we dig up. It's not only going to CO2, but only into the also into the oceans, on the land, destroying land. We're exhausting stuff on a great scale, and only looking at CO2 is too meager for me. So directly cutting in what we dig out from the earth, that would be good.
Yeah, well, that's a nice addition. Thanks. Thank you, Peter.
If I may, I can have another addition, and that is I'm extremely worried about global trade where companies produce oil and buy weapons instead. The large weapon industry is outside our focus, but it's estimated that weapons and army have at least 20% of world economy.
Yeah, this
huge.
has also connection to this political unrest. In fact, what Simon was posing, I guess.
Yes, I'd like to add that I'd like to keep it focused on energy for this conversation.
Yeah.
We have only an hour to get to world peace.
Yeah,
so,
let's go to the next proposition.
Yeah.
Eva. Well, then we are now about the main challenge with energy transition. And we have 4 potential answers. One is the citizens are not going to want to change their habits and buy more expensive technology. B is to make it truly global, only rich, the first world countries will be able to develop, deploy and benefit from sustainable energy technology. C is dealing with intermittent sources, such as solar and wind will always lead to considerable cost for conversion and storage systems. And the last one is to avoid lock-in effects.
But perhaps it's good to also discuss what are lock-in effects later.
I would like to see hands, because I guess that everyone knows what lock-in effects are. Who does not know what lock-in effects are? They don't dare to ask. There are some people that don't know. Well, explain, Adri.
Yeah, so a lock-in effect is an effect where you take a decision now that seems decision now to regret it later, because it really leads to a suboptimal solution. For instance, investing in expensive infrastructure that is going to be not as valuable as it turns out later on is a good example. But what worries me, for instance, in the case of the Netherlands, is that we have this very nice infrastructure for gas, for natural gas. Yes, but that's I think it's also a lock-in effect. If we rip out that natural gas system now, then anything related to it that may make use of it in the future is not possible anymore.
I understand what you mean.
But that would then rather be a lock-out effect.
Yeah, lock-out.
Yes. Yeah. But you're locked in. You could also say, Niels, that you're locked into a solution which no longer includes basically a natural gas infrastructure. It's just how you look at it.
Yeah, I agree.
But if you look at the answers, you see that only 12% answered this last one, but the others all are higher cost, higher cost, higher cost. Can you comment on that? Do you really think innovation we do relates to higher cost, or could we also see it as a nice challenge to get nice new technologies that would reduce the cost? Adri.
Well, the way I look at it, also in relation to what we've just seen, I mean, I agreed with the previous slide and the response on the previous slide. Yeah, I think that I think there are two options. I think there are plenty of options to make new technologies more cost effective, to bring the cost down of new technologies. That's one. But even if they tend to be, let's say, initially more expensive, what is the cost of not implementing those new technologies and allowing basically for the whole planet to heat up? I think the costs associated with that are even much greater. Yeah. So I would not like to. Yeah, I would like to put it in isolation.
Yeah, but Simon, because I can imagine that you are definitely working on something that reduces costs.
Yeah, I think an interesting phenomenon that we see on a company-wide scale. So, take a typical multinational, 50,000 people work there, active in let's say five countries in Europe and so on. On that scale, what we see is predominantly there's technical reasons why new technologies are not adopted, but I think a very interesting one is the cultural element. And to be more specific, I think the capabilities trap and worse before better behaviors are two elements that I think are increasingly being brought to the forefront as, I would say, challenges to adoption of new technologies. And with
can you repeat that? Worse before better, and the other one
worse
was
before better behavior. So what it typically means is that before something gets better, it gets worse. Right. So and in our case, we produce systems that reduce energy waste and increase reliability of industrial electric motors. Who wouldn't want that, right? And but still, not everybody is using our technology. And a key element in that is that there's a cost of changing, right? So there's changing costs, and what you usually observe is that to benefit from all this wonderful technology, you have to learn about it, you have to invest in implementations. So the cost goes before the benefit. De kost gaat voor de baat uit. And that,
so in fact, you mention a lot of more challenges that goes with energy transition, like education. Yeah. Mr. Kruse also misses a point. Before going to Niels, who misses a point? Mr. Kruse, V. Kruse. Yes, hello.
Yeah, this is more to do with the scale of equipment required to produce certain amounts of energy. That in terms of sustainable or for the energy transition, that you would require much larger pieces of equipment, much larger use of aerial or land or sea to get the same amount out. And that's something I'm missing in this poll as a point.
You mean that the energy density is quite often
energy
lower?
Density, yeah, that's exactly what the correct term.
Yeah. Niels, can you react on that? What about the metal fuels? How about the energy density of the metal fuels, and how big should my CHP be if I use metal fuels instead of natural gas? Tell me.
Well, the good news about metal fuels is it's extremely dense. So you can store an enormous amount of energy in a very small volume. So that's one of the strongholds of metal powders. Really, if you high temperatures, so that's where they really find an application. But to respond on the question here on the screen, I think in the end, for both countries, but also normal people, what really matters is cost. So if you make things cheaper, they will move in the right direction. But that's very tricky because I think today our Parliament agreed on an item that they wanted to have an energy transition in the Netherlands, that all the Dutch households, they switch off from the be cost neutral, which means it doesn't cost anything for the citizens in the Netherlands. Now that sounds very nice, and they actually all agreed that we should do this, but it will have a cost. Somebody needs to pay this. And so it's very easy to say, just make things cheaper. I personally think you should make the options that you do not want, you should make those more expensive. So essentially putting
make fossils more expensive, in fact.
Yeah. CO2 penalty, I think, is the way to go if you really want to make a change.
Yeah. Okay. I have one last question of Nandalal Kirichandram. I don't know whether I pronounced it right, but
no, I had raised my hand for the lock-in effect that time.
Okay. Well, please, to all people, put your hand down. That makes it a bit easier. Thanks. Then I would like to go to the last poll because we have only 6 minutes left. And that one is on the future energy use of industrial plants. So the question is, should it focus on electrifying everything or intensifying technologies to make production processes more energy efficient? Should it focus on increasing the synergy between the different businesses, means like exchange of energy, low caloric heat and energy? Or should it focus on changing from large scale centralized continuous processing to smaller scale distributed on-demand processing and only produce it during the day, because then we have the energy? Well, in the beginning I thought it will be another balance, but it looks in fact that intensifying the technologies to make the production processes more efficient gets a higher one. I would like to ask Tim, what answer would you have given here?
I'd probably go with the masses and go to B, intensifying technologies to make production processes more energy efficient. Especially at this point, I think that's very important because I mean, what we have to keep in mind is we can have all kind of new technologies, and then we can build all kind of new plants. But you know, building an entire new plant is not very good for the environment, even if that plant is a bit more energy efficient than the old one. And that is an important factor to take into account. So I would go for B here, and not just develop new technologies to build new plants and new processes that are energy efficient, but also to make ones that are currently used more sustainable.
That's a nice challenge because we have a quite expensive installed base in there. But wouldn't it be more relevant to do all of them? Niels?
Anita, I think I disagree with Tim. We should, of course, it's nice to intensify existing technologies. That's always good. But what would be even better is to decarbonize. So most of our chemical production is still fossil based. So we will run out of fossil resources. We have the global warming, so there are plenty of reasons to defossilize. So I would go for option A, and that's maybe a bit. There are also processes where you should really think twice to electrify, but broadly speaking, I would say electrify everything.
Well, now I'm curious, Simon, what would you say?
Well, again, I'd like to add number E.
Good.
I think a good start, or a very practical start, is to start implementing all the technology that's already available in industrial processes to reduce energy waste. When you look at a typical production site, 80% of energy goes to industrial electric motors. On a global scale, around 30 to 35% of all electricity consumed goes to industrial electric motors, operating pumps, compressors, and so on. There are IE5 motors available that greatly reduce energy waste. Yep. They're just not being implemented. In the Netherlands, we have lots of projects where the government is responsible for making sure that companies adopt these new technologies, but the government is not really chasing that adoption. So we have lots of paper tigers, and I would suggest that a real quick win is to focus on implementing and making sure that companies implement the technologies that are already available.
Well, that's a nice one. I heard that there's also somebody else who has something to add. We heard him earlier, Nicole John. What did you want to add?
Yeah, hi, thanks. I wanted to point out the connection between this question and the previous one, because for me, options A, B, and C still create so-called lock-in effects. So if you're electrifying something, you're locking into a particular pathway. If you're increasing energy efficiency of any process, you're also locking in those systems and making it harder to transition from them. And if you're creating synergy between different processes like industrial symbiosis, you're also creating very highly interlocked sites and systems that also make it difficult to change. So that's why I think, unless you're very clear about which pathways are the best, option D, even though it's not the most efficient, helps minimize lock-in effects.
Yeah. Well, anyhow, it shows that we need an integral solution, including all of these. I have one last one, because then we really have to move on. And wait, maybe Eva is really chasing me now also, but I want to have Peter Dodi. We heard him before. Please, shortly.
Yes, I put it also in the chat. For me, it's all about cost. And so we need to analyze all kind of pollution and all kind of effects that are caused by technology in such a way that the damage can be repaired. And then the cost of number of technologies will rise enormously, and then we can find the best alternative and let the market do the work. We cannot select now. We don't know the cost of what we are saying.
No, that is true. It's true, but it's also depending probably on what our government is doing, what they are going to stimulate, cost-wise, subsidy-wise.
And what the Russian government is doing and the Chinese
Indeed.
government. So you
Indeed.
have a kind of political edge there.
Yeah. Okay, I would like to finalize this session. I would like to thank the keynote speaker and the panelists, and of course Johan and Eva and sorry, Valeria for the preparation of this session. Next, there will be a networking session. You were all communicated that you can continue to these networking sessions and that you would get a separate link, but there is no separate link because there's only the one networking session. The networking session will continue here, which means that if you don't want to join the networking session, you may leave. This networking session, there will be some presentations of researchers in the engineering field. So you see them on the screen now, Jorrit Bleker and David Fernandez Rivas. And they will tell about their research and you may further connect to them. So I would like to thank you once all. Stay if you would like to stay hearing about them, or otherwise you may join. And yeah, be informed that there are more of those kind of webinars. The next one is on the 11th of November, and that's a circularity webinar moderated by Kees Roest. And every week there will be a webinar, so look at your email, you will be invited and you can join. Thanks a lot, and till next time.
Thanks.
Thank you, Anita. And now Johan Padding and Valeria Garbin will take over.
Yes. Johan,
yes, we will.
Thank you very
turn
much,
on your
Anita.
camera.
Yes.
You can turn on your cameras. And
I don't see Johan up yet.
I am here.
Yeah, I don't see on the screen. But,
okay.
in the meantime, are there any other PhDs or researchers who would like to take the stage?
So I think it's good if we can already ask the first speaker. So that was Jorrit Bleker to already share his screen. So that's at least can check if that's working. So are you here, Jorrit?
I'm here. So
hi, welcome.
Screen 2. Yeah, I think this should work.
Yes.
All right.
Yes, it's working. Yes. No, we see your.
Oh, I see the presentation.
Presenter screen. Yeah.
Wait.
Yeah, that's better. Yeah.
Perfect.
And Jorrit, maybe you can start with a short introduction of yourself.
Yeah. So I think the audience is a lot bigger than I expected. But hello, everyone. I'm Jorrit Bleker. I recently started my PhD in April in the TU Delft in the transport phenomena group of the chemical engineering department. And I'm mainly looking into how to improve mass transfer in electrolysis by using pressure variations. So can I start already, or?
Yes, I think it's good to start. As there's still some people coming in who join especially for this one, but I think it's good if you already start.
Yeah.
Yeah. So for alkaline electrolysis and for CO2 reduction, we are converting, for example, water into hydrogen and oxygen, or CO2 in carbon monoxide and oxygen as well. And there's a big factor here, and it's the low solubility. And the low solubility of these gases that are forming, they create a lot of bubbles. So yeah, this is just a small electrode in a beaker, but you can see lots of different bubbles of different sizes. And these bubbles actually cause quite a large resistance, so we want to get them off as quickly as possible, but also they are our product, so we want to have as much bubbles as possible. We just don't of the electrode. So in order to remove them efficiently, I'm making use of pressure. And the effect of pressure on a bubble is if we have a high pressure, we are compressing the bubble, so you have a small bubble. And if we're reducing the pressure again, you're increasing the size of the bubble. And if your electrode is full of small bubbles and you suddenly reduce the pressure, all of them will become big. And this is what we call a pressure swing. So by reducing the pressure, all of the bubbles will increase in size, and the buoyancy forces, they will take them off the electrode. But then if you do this very quickly, you also can cause something else. So if you have a quicker swing, cause a bubble to increase and decrease in size, and you're actually creating a local mixer with the electrode, especially for CO2 reduction, where the solubility of CO2 is also quite low. You could create local mixing. So in the coming 3.5 years, I'll be looking into this.
Thank you very much, Jorrit. Now we take questions from everyone in the audience. We have already seen a very active participation, so we hope there will be more questions.
Yeah, I see an S. Pau raising his hand. Is that Stefan?
Yes, hello, Padding. Nice to see you again.
Yeah, nice to see you again.
So I have a question to you, Jorrit. You just started your PhD and you're going to look into the effect of pressure, also with respect to the drift of the bubbles, which can have also a mixing effect. But is your focus also on the process efficiency? Yeah? Because if you have to operate this mode in pressure swing, then also the energy efficiency of the system can be affected as well.
That's true.
Compressors and expanders and everything. So how do you take into account? And is this also a partial focus of your study?
So the PhD project is based on an initial paper written by my supervisor David and a master student. And you can actually reduce the total energy efficiency of the process, or you can increase efficiency. So the pressure is a relatively, I don't know, weak physical force, so it doesn't take a lot of energy to increase the pressure of a liquid. So the pumping energy of reducing and increasing the pressure is it's less than the energy you gain by removing the bubbles quickly. Of course, what you're also talking about is the compressors and the afterwards. And yes, this is something I still have to look into. So it might turn out that maybe you can, by just having a small pressure decrease, for example, going from 20 to 18 bar, you can remove already a lot of bubbles, but I don't know for sure yet.
I think if I can add to this as well, first look at the physical phenomena. What is the real increase? And I think also the characteristic length of the electrodes can have on this fast-moving bubbles near the electrodes, and then move to the overall evaluation of the process. I think that's the right strategy to go for. But perhaps Johan can add to that, or?
No, to be honest, I was actually having a look at the chat and everyone who wants to ask questions. So that was my task right now. But yeah,
I think Niels is next.
Okay, thank you. Thanks. So it helps to click the hand button. Jorrit, very interesting idea to work with varying pressure. So I can imagine it will have a lot of effect on the bubble action and also all the processes close to the electrode. I wondered if you already have some idea of the frequency at which you would like to apply these pressure fluctuations, or in other words, what typical time scale is important here.
So I don't have the calculation by hand now, but it's in the order of 1 Hertz. So it's around 1 hertz, and that when you increase the pressure, for example, from atmospheric to 3 bar, you get a bubble interface that's moving at such a good, or at a speed that's enough to mix up the boundary layer for CO2 reduction. Or let's say because you have diffusion coming in, and then this interface speed should be enough to create enough mixing to mix up. But I don't have the calculation by hand, so I can't give you the exact numbers. But it's in the order of 1 hertz, so one time per second.
Okay, yeah, I get the idea. I was just curious what time scale it is that you want to agitate, so to say.
Yeah, so it's actually not ultrasound. This is something called infrasound, because we're operating below the audible spectrum.
Yeah, I see. Okay, thanks, Jorrit. Good luck with your work.
Thank you.
Okay.
Yeah,
then
I think we may have time for a couple more questions before we move on to the next presentation. What do you think, Johan?
Yes, I think so. The first next one who raised his hand was Peter Dowdy again. So Peter.
Yeah, again. Thanks. Well, the first thing that struck me in your presentation, small presentation, is that everybody assumes that you need to do the separation of gas and liquid inside your cell. That's kind of basic assumption. But why not work at higher pressure so that you have dissolved oxygen, hydrogen, or whatever, and pump that around? So that could work too. And to add that if you start pumping around, you may generate turbulence. And you can do that on purpose by having some blunt objects between the plates so that you get small vortices. And that would also generate pressure fluctuations. And that's really cheap. And finally, if you go to pressure fluctuation of 3 bars, you need to worry about the integrity of your membranes, because 3 bar on a large huge force.
Yeah.
And you will compress the gas too, so you spend a lot of energy.
So if I go from the last point back forward, so we have the same pressure on both sides of the membrane.
Yeah.
So in this case, you won't have a differential pressure across the membrane. So the forces on the membrane should be relatively small. But this is an operational challenge, because we need to make sure that there's no huge pressure difference across the membrane.
And that's difficult. I don't know how you would do that technically.
Yeah, so I've currently designed a setup. So the only thing I've gotten so far in my PhD is to actually generate the pressure differences. And I now work with 2 magnet valves which open exactly at the same time, and then the pressure is coming from an expansion tank. So that should relatively generate the pressure at the same speed. So hopefully in both compartments I will get the same pressure at the same time. But yeah, I don't know. I haven't actually, I haven't gotten the actual flow cell yet, so I have not been able to do the full experiments yet.
But you can do a sensitivity analysis and see if you miss the timing by 1 millisecond on your valves, what the pressure fluctuation is across the membrane.
Yeah.
And then see whether that's acceptable.
Thank you, Peter, for the additional input. I'm sure Jorrit knows where to find you to follow up for some more input. So. We need to take a couple more questions before we move on to the next presentation. Thank you. I think we can take both questions. I don't remember who was first. Let's start from...
Was, Adrie Huisman was the next one who raised his hands. Yeah.
Great.
All right. Yeah, thanks, Jorrit. I really enjoyed your short presentation. I was just wondering, and Niels also asked a question about basically how fast do you want to do this. That's pretty fast from a conventional process point of view.
Yeah.
And I think what you will need to deal with then is basically these dynamics, these pretty fast dynamics of 1 hertz. And I think what is challenging then is basically the gas cap, which is typically in top of your electrolyzer. Because it's one thing to make these bubbles by pressure variations bigger and smaller by 1 Hertz, but that also goes, of course, for the gas cap in top of your electrolyzer. And that basically adds to the inertia of your system. So I think you really need to take a very good look at your overall system system design, including the resulting dynamics. Yes.
True. Yeah. To quickly go back on this, I'm planning to have a full liquid cell. So the picture was just an illustration. I'm planning to have a completely filled cell filled with electrolyte, and the only gas that will be in there is the generated bubbles. But they will still buffer. They take up some of the energy when you apply pressure to them, so they could slow down the process. And I don't know by what sense they will do that yet.
Yeah. Okay. Thanks.
But thanks for the feedback. Yeah.
Very good. Then the last question that I would like to have is from R. Raman. He raised his hand. He or she raised his hand or her hand. Hi. Hey. Yeah.
Hi. Your work is really interesting, and I work on something similar. I'm a PhD candidate at UTwente. Do you see this more applicable at higher current densities? Because then you're limiting your reaction is limited by the concentration of reactants.
If you and do you mean this for CO2 reduction or for alkaline electrolysis?
Yeah, for CO2 reduction specifically, because there you have a competition between water reduction as well.
Yeah, so especially the faster pressure variations, I think they are more valuable for CO2 reduction because, as you said, it's rate limiting there. And I think in the normal circumstances, it's about 40 milliamperes per square centimeter. And we hope to achieve, at least the double by having these local mixing effect. And the nice thing about having a bubble that's moving is you're actually creating the mixing in the place where it's needed the most, which is right at the electrode. So I hope it will. Yeah, I don't know. I haven't tested it yet, but I hope we can at least achieve the double production rates.
Okay. I think we need to move on to the second speaker, and that's David. So David Fernandez Rivas, are you here? I do not hear something yet.
He was there just now.
We see him online, but
okay. So let's wait a little bit. Yes, okay, you're there. Okay, so can you share the screen and open the mic and the camera? Thank you, Jorrit, for your input. Very interesting work. Ultra short pitch. We cannot hear you yet, David, so perhaps look at your microphone. I think it's off.
You can turn it on in the Teams window.
We can see ourselves now.
That is weird.
Yeah. Okay, we can see your camera there.
Hi, David. Now we cannot hear you.
It might help if you leave the meeting, enter again, because it would be a pity if we cannot hear you.
Yeah. Okay, so let's wait a moment.
Okay, let's take a 2 minutes, 3 minutes to for a toilet break, and so
that's a good idea.
Yeah,
2 or 3 minutes. So I'll see you all back again in 2 or 3.
Hey, David, we cannot hear you yet. Can you say something?
So David is still muted.
It's really an ultra short presentation.
Yeah, we see now that you're muted, David.
Mm-hmm.
It wasn't the case previously.
Okay, so that's better. So
Yeah, so go to Teams.
we can help live. Yeah.
Oh, yeah. That's weird because it says that maybe you're try to unplug your earphones, your microphone earphones.
Oh, they are unplugged.
Oh, they're already.
Okay.
Okay, then this is a pity.
Yeah, this is a pity, and I think that at this point we have to admit defeat by technology.
Well, we can continue, and maybe David will be able to answer questions. No, that's going to be very difficult.
Yeah.
Try connecting with your phone. Yeah, that's a good
So I
good
think
idea.
you're maybe not muted on Zoom or on Teams, but your microphone is just turned off. So if you change your volume settings, you should.
Yeah.
Mm-hmm.
Maybe your microphone is in the camera or something. So maybe
No,
you can go to the settings and pick up the microphone from the computer. Can you hear now?
Yes.
Ah. Oh.
Okay, everybody unmute.
Yeah, so now I put mute on the laptop. And if somebody speaks, then...
Yeah, but we can hear you now.
Right, so now we have audio through the phone and sharing on the screen, right?
Perfect.
All right. So we'll very short introduction. I'm David. You might be tired by now to see that slide. It's nice that the previous presentation was about bubbles, because I also wanted to talk a little bit about bubbles. And I entered this field of electrochemistry by addressing problems caused by bubbles. And well, over the past 5 years or so, we've been looking at not only at the smallest scale, but we also try to look from a larger scale and where these sort of renewable energies could have an impact. So I can send later these slides if somebody is interested in looking at this problematic. So I think connects to what the previous panelists were talking about. So what the conclusion from that event, or what we did back in the day, was to identify that this is already the most viable solution to create, in this case, solar hydrogen. But in the future, this sort of integrated approach could have a higher impact. So since I work in microfluidics, I always get the question, so like, are you really sure that you want to talk to process engineers and large scale engineers? Because I mean, typically, well, people are talking about tons and I don't know, kilograms, and in microfluidics, typically, well, it's a few grams or micrograms. But if you look at where the most fundamental phenomena take place, is actually at the mesoscale, so it's from nano to micro. And we've been defending for a few years now that is actually here where we could innovate or bring new solutions to well, the industry or the market. And this connects somehow to something I will have probably a couple of slides at the end on process intensification, which can be seen as innovation, right? Now, going a bit more into detail to give you a bit of a flavor of what we're trying to do here in Twente, is to look from the fundamental aspects of how a bubble can affect electrochemical processes, and sometimes propose mitigation techniques. For example, the previous speaker was talking about infrasound. So we're actually looking at ultrasound to try to remove or improve the mass transfer of a bubble phenomena at an electrode interface. Of course, you can see in details later, we have published a few articles on this. And well, these experiments are relatively boring if you ask the PhD students that look at it. So actually, Akash just made a question before, so he's working on this project. So we make specific surface modifications on an electrode, and then we look from the top at how a bubble grows, and we modify specifically the surfaces to guarantee that there's always a bubble there. Not always that's the case, but most of the times we are successful in that. And then by looking at the radius time curves, we can understand a bit more of what is happening around this bubble, or the gas evolution around this electrode. And well, then not to make it too complicated, I already took too much of your time. So Akash just spoke now. We are now looking at new type of electrodes to well, improve somehow the efficiency of hydrogen generation. Since I saw some names in the people's list, I saw some names already left, but I think it's interesting now to connect to what you guys might be doing on process intensification. And we recently made a new type of definition of what it means. And what I want to draw your attention is to let's say, the possibility to innovate or improve existing processes. So this obviously connects to the UN Sustainable Development Goals, but can be applied at almost any level. And probably some of you might recognize the work from Stankiewicz and Tom van Herven here. And well, we think that we as educators or professors at the university need to think of the best ways that we can educate the engineers of the future on how to innovate or intensify processes. That's a word I also saw in one of the previous speakers. And well, this probably takes too much to really explain now. I think I should just wrap it up, and thank you for your time. And well, if you have some questions, then I'm more than happy to answer.
Thank you, David. That was indeed really quick. I like the fact that you explain that even for the large scales, it's really important to consider, let's say, the mesoscales, and then that's also indeed in my work also a thing that I always like to explain to people. So I'm there with you. So are there any questions from the audience already? And I think by now we have a small enough audience that you can just unmute yourself and ask the question. You don't have to raise your hand anymore. If not, then I actually so to use ultrasound to control, let's say, the size of the bubbles, that they start to grow and become smaller again. But doesn't that actually also influence the surfaces of your reactive elements? So doesn't it damage, let's say, the materials?
So that's an interesting question. So we haven't really looked yet at combining electrolysis and ultrasound in the experiment. So we first start with electrolysis, just looking at how bubbles evolve.
Yeah.
Understand how they interact. No, sometimes if they grow close to each other, or if you change the current density, can we well, prevent how to say, undesired phenomena? The idea with ultrasound has two how to say, pronged approach. One is when you use relatively low pressure amplitudes, you might just induce better mixing and well, just mildly agitate the system.
Okay.
If you increase a bit more, then of course you might have some sort of cavitation, and then the implosion of bubbles eventually lead obviously to jetting against the surface of the electrode, which could be beneficial in some cases when you have some sort of contamination, or the surface of, for example, a catalyst has been somehow poisoned or covered. We haven't got to that level yet.
Okay, yeah, good to know. Thank you. Are there other questions?
Yeah, I have a question, if I may. Thanks, David, for your presentation. I was just wondering, seeing your presentation, do we have a clear understanding how actually a bubble grows? Well, I guess we do, but how it finally detaches itself from the surface? What do we know about this from a fundamental point of view?
Yeah, so there's been a lot of work, not only done by me, but also in the physics of fluids group. The challenges to observe the last instant of a bubble detachment are very high, because typically it happens at very small scale and very fast time scale. So depending on the contact line pinning conditions, you might have sometimes like some very, I have some slides somewhere there, so some necking, so that the bubble, let's say, due to the theoretical Fritz radius, should have already detached a long time ago, but somehow due to some, how to say, obscure phenomena we haven't identified yet, sometimes the bubble can pin there or detach before that time. And yeah, we don't know exactly in that last instant how it's really happening. But well, we are getting closer with the fast imaging and microfluidic tricks to try to control where this contact line is pinned, because that is crucial.
Okay. Yeah, the reason why I'm asking is that if we really have a fundamental understanding, it would also help us basically to design better actuating mechanisms to actually allow for this to happen sooner and better.
Yeah. Yeah, so one very simple approach that we have seen in experiments is sometimes put two of these pits relatively close to each other, so that when two bubbles start growing, they will just detach before they are too big to start depleting the gas in the surrounding medium.
Okay.
But of course, there are many other tricks. You could have some sort of self-resonating structure, so that when the bubble is sitting there for a while, and you have some sort of underlying vibration, and eventually you can hit some resonance mode, and then you would just flip it off. Well, there's a lot of room for innovative experiments there.
Okay, thank you.
Okay, thank you. I think by now it's already, let's see, 5:30. So we need to stop. I would like to thank you all for the input. So also in this last part, because we were actually only expecting about 10 people or so in this part. So it's really good to see many more in here. So I'd like to thank, of course, all the speakers. So especially the two of these last parts as well. So Jorrit and David, thank you very much for your input, and also the audience, of course, for their inputs. And see at the next webinar, which will take place in exactly 1 week from now. So next week, Wednesday again, and will be on circularity. So is there anything that I forgot? I'm looking at Eva or
No.
Valeria.
That was very clear.
No, I think that's it. I will try. I'm trying to share, but my laptop is no longer willing to share anything. One final remark. If anyone would like to connect with one of the presenters or one of the panel members, you can always connect with each other on LinkedIn, of course, but you can always also send me an email. I work at ISPT. I've shared my email address in the chat section. It's eva.verbeek, VERBEEK @ispt.eu.
Yeah. Okay.
Thank you very much, everyone.
Thank you.
Thank you, everyone.
And see you all next week.
See you next week. Bye.
Bye. Bye-bye.